Hello there and welcome to this course on hyperparameter tuning for healthcare with Python. My name is Valentine and I'll be your instructor. In this course, we are going to be learning about this process called hyperparameter tuning. It's an advanced technique that we can perform in order to improve our machine learning model performance. So we might decide to create maybe a machine learning model to predict a particular outcome, whether patients are going to survive or not. Then in an effort to create a best performing model, one of the techniques that we can be able to perform to ensure that we have a better performing model is to look for those optimal values for hyperparameters. So the machine learning models normally have what are called hyperparameters, which are more like settings. So we need to find the best values, the optimal values for those settings, for those hyperparameters that will lead to our best performing model. So by the end of today's workshop, you should feel confident enough to undertake several techniques that will allow you to get those optimal values that you would want, that would essentially help you to achieve a business objective that might have been set. So yeah, so that's the idea of this workshop. If you're a beginner, we would recommend that you look into just Python introduction courses before going into this one. This one is a bit more advanced. Then after that, you can go into some other data analysis or data visualization courses, as well as regression or classification courses before now coming to this particular workshop. So yeah, so let's get started. The structure of our workshop for today will be as follows. We'll start working on just understanding the learning objectives. So understanding what by the end of this particular workshop we should have achieved, we will have achieved. Then talk about hyperparameter tuning, as well as just those different techniques and why we would want to perform it. The idea is that we should have some theoretical understanding of those techniques before now going into application using the Python programming language. Then after that, we'll go into a practice session that will entail using Python, and we'll focus specifically on using the scikit-learn library to perform hyperparameter tuning techniques. Then towards the very end, we'll just talk about what's the next step. So once you have learned how to tune your parameters, what should you with regards to the model that you're working with, what should you look towards doing? So yeah, so let's get started. By the end of today, we expected to have achieved these learning outcomes. We should be able to describe the role and importance of hyperparameters in machine learning models. We should also be able to implement different hyperparameter tuning techniques to improve model performance. We should be able to evaluate the impact of hyperparameter choices on model performance and interpret those results and make recommendations for model improvement. Do note that all these learning outcomes are within the context of healthcare, but you can also apply them in other contexts. It's only that this workshop will be focused on just using data sets as well as problems in relation to just healthcare. So what is hyperparameter tuning? So hyperparameter tuning in healthcare with Python involves optimizing the parameters that govern the learning process of a machine learning model, and essentially to improve its performance on health-related tasks. So essentially this process entails looking for what are called hyperparameter values, models or machine learning models. Say for example, if I do get to share my screen, I'll just go to the documentation, so I can just quickly Google random forest, and you can also do the same thing, random forest, maybe sklearn. So we want to get to see the hyperparameters for the random forest classifier. So, or you can also do the same case with a regressor, any would do. So once we get to the documentation, whenever we are using this model, whenever we want to create it, we would normally set what are called hyperparameters, or the values for those particular parameters. So a model like random forest classifier has several hyperparameters. So the first one would be n estimators, the other one would be n criterion, the other one would be max depth, etc. So these ones are what we would refer to as hyperparameters. So for example, a bootstrap is hyperparameter, mean width fraction underscore leaf is, again, a hyperparameter, and they take values. So for example, for this hyperparameter that you see, mean, weight, fraction, leaf, takes an integer value, or estimators also takes an integer value. And you can see here, an estimators takes an integer value, but default is 100. And as n estimators just means the number of forest in the forest. So if you were to just understand a bit more of how random forest classifier works, it uses multiple decision trees, which are also another type of it's another type of algorithm, and you can create models which are called decision tree models, and random forest classifier uses multiple decision tree models to make predictions. So generally what you would be doing when you're using a random forest classifier is to use the outcome of multiple decision trees to make a particular to make a particular prediction. So if you're going to be using random forest classifier and maybe it uses 100 trees or 100 it could maybe even 10. It could be it's using just 10 decision tree classifiers. In that case, if 9 out of 10 of those decision tree classifiers predict that an outcome should be a 1, and there's only one decision tree that predicts the outcome to be a 0, then it means that the random forest classifier will take the majority voting, the majority predictions, which would be the outcome that would be 1. So the random forest classifier would actually predict the outcome as a 1, because a majority of the decision trees, which are what we would refer here, number of trees, are the ones that have given that particular outcome. So for each algorithm, this is just one. Random forest has several, and we can visit the documentation to get more information about those parameters. But our focus is to look for the set of hyperparameter values, whether it's 100 or 99. It could be this, the criterion here is Gini, but when you look at criterion, there are several values that we could use. There are 3. So this process of hyperparameter tuning entails looking for a combination of the hyperparameter values that give the best performing model. That process can be tedious if you were to sit down and do it manually. Sometimes it could work if you have some domain knowledge or expertise in a certain area, especially if you've built previous models and you already have an idea of the optimal parameters that have worked before, and also with the data set that you have. So in many cases, that process can be tedious, but we perform now hyperparameter techniques to automate that process and be able to get the best performing models. Again, still, it might also be tedious, but it's a sufficient way that we can use. It's a good way that we can use to just be able to get those optimal parameters. So that was just a quick overview of what those hyperparameters are. So just going back quickly, just to further just go deeper into understanding what this process entails. So we can perform hyperparameter tuning with just a range of different tasks, whether it's predicting patient outcomes in the context of healthcare, or it could be also diagnosing maybe diseases, maybe based on medical data, etc. And it could not only be just for classification problems where we're trying to predict a categorical variable, but we could also be predicting a numerical variable or continuous variables in the case of regression tasks. So you can always perform these techniques that we're going to be working with in such situations. And we've already seen what hyperparameters are. These are just configuration settings that we can use to adjust how the model learns. So the different tuning, the different hyperparameters, they have different meanings. Like you could see for random forest, there is the n estimators, and there are quite a large number of them depending on the specific type of model that you want to build. You could find that in random forest, you will find that in random forest classifier, the parameters are different than what you would in logistic regression model or in a KNN model. They all have their own different parameters, but again, when you're doing this process of hyperparameter tuning, you need to visit the documentation for that particular purpose. These model parameters would basically be ones that are learned from data. So you would need to set them before training. So when you're instantiating your model, you would need to set them up. You do not necessarily, of course, have to use all the hyperparameters, and you could always set maybe just a few to just test out their values and see whether they lead to a better performing model, and before you now continue to use others. And before even getting to a process of hyperparameter tuning techniques, you would need to ensure that you've also tried other types of models. That way you are sure that this model that you want to further optimize is the best performing of all the models that you have at your disposal. That way you don't end up tuning a model that isn't best suited for your data set. And not only can you take this particular way of hyperparameter tuning to improve your model performance, but you could also decide to perform what is called feature engineering, like ensuring the data set is in a better format, or getting more records, or even just dropping records that do not improve your model's performance. So there are other ways, but again, this is usually one of those ways. Once you have already even performed feature engineering and you do not note any sort of change, you could now move on to hyperparameter tuning to ensure that you get a better performing model. So yeah, in terms of benefits of hyperparameter tuning, improved model performance. So if you perform hyperparameter tuning techniques and you get hyperparameter values that are suited for your case, then it means that the model that you have would be better in terms of making predictions. There's also efficiency in model training. That's one of the benefits. So by optimizing hyperparameters, you can be able to train a model much more efficiently and be able to reduce computational costs and time. And also at the same time, as each data set is usually unique, hyperparameter tuning just allows us to be able to specify our models or to customize our models to specific data sets. It just means that you cannot just take one particular model and take it to a different data set and use it as it is with the respective hyperparameters. You need to ensure that it's tailored towards that data set. So if in the future you have more data, you could always just ensure that the format that you're giving to that model in terms of that data is the data that was initially trained to the model that you currently have already tuned. So there are many benefits. These are just a few. The types of tuning, hyperparameter tunings, techniques that we're going to cover are these ones: grid search, random search, and Bayesian optimizations. These ones are the basic ones. They are the ones that would highly give you the outcome that you need. There are others. Even a basic one would be manual search, where you tend to put the parameters that you want manually, but that's an exhaustive process. We won't go through that, and you could always do that by yourself if you want. But these ones are the ones that we're going to learn, the automated techniques that we'll get to learn. We'll go through each and every of these techniques in the next 2-3 minutes, just one by one, just explaining what each entails before now moving on into the practice work. So let's get started with the first one, grid search. So grid search majorly is this particular, I can even just go through the definition because I haven't put the definition in the slides, but grid search involves just being able to set, first of all, defining what is called a grid. A grid would contain a set of parameters. So for example, you could have to, maybe in the case of random forest classifier, you can use an estimator, and you could as a parameter, and you could specify the values that you would want for that. So for example, in our case here, we have n estimators, 50, 100, and 150, and also we could also define inside that grid we want max step to be 10, 20, 30, as well as mean samples. These are the values. So assuming that this is our grid, this grid would contain the values that we would want to check for and see which of these values, if they were put into a combination, which combination can we get from these values that would lead to a better performing model. And what grid search would do, which we will implement, it's an algorithm that we are going to implement in our we're going to use in our problem in a few. What grid search will do, it will look at all the possible combinations specified within the grid, and then it will take the best performing one. So for example, it will look at 50, 10, and 2. Yeah, that's the first combination. The second combination can be 50, 10, and 5. Then 50, 10, and 10. Then after that, we can move on maybe to the next one, 50, 20, 2. 50, 25, then 50, 20, 10. So those are different combinations. So what grid search would do, it would be creating different models and checking which model actually performs best, and then retaining that set of hyperparameters until it gets the best one. So generally it will check all the possible combinations that we have specified. So for example, in our case here, we would have we would have actually 27 combinations, because we have, for n estimators parameter, set 3 values, for max depth parameter specified 3, as well as for mean sample split. So we would check for 27 combinations. Again, if you have many, because you have many parameters, as in the case of random forest classifier, which we saw here, we have many parameters, and we would need to check for that. So but it's an easier way. It's an easier way to just quickly get started. Sometimes it works. You might get to achieve your metric of success, which, so for example, if you wanted to achieve maybe 0.8 as the metric of success, and you have a model that's at 0.75, and somehow once you've performed grid search, you might end up with maybe 0.81 with one of the combinations. Then you can use that, which is fine. But again, you can start out small, then later onwards expand if you feel like you have resources to be able to go through all the possible combinations. So the process generally would involve just being able to go through all the possible combinations and get the one that makes a model that performs really that performs well than the others. And it also uses a process called cross-validation, where you use just different subsets of your training data to be able to perform this process of just hyperparameter tuning. That way you do not face a problem that's called overfitting, where a model learns too much from noise within the data set, that when it comes to new data, it performs poorly, but when it comes to data that looks closely like the training data, it performs okay. So it also ensures that you do not face what is called overfitting. And yeah, so that is just a quick overview of grid search. On the other hand, random search is somewhat almost similar to grid search. The only thing here is that the process of getting the actual combinations to work with, it's usually random. So what happens is that, yes, you could have defined your grid, but in this case we call that as you could not necessarily a grid, but you can just have like a range, or let's say you want maybe or distribution, maybe for n estimators you want to check for values between 50 and 150, or max depth from 10 and 30, or 2 and 10, for mean sample split. Then you can be able to, first of all, initially when you're starting out, specify that you want to try 20 different combinations, or alternatively you can specify how many times you want to check for a set of combinations. So for instance, initially you might decide to set that space, that hyperparameter space, that you want to check for those combinations. Then you would randomly, the algorithm itself would select combinations, not from the very beginning. It would select random combinations of hyperparameters within what we have specified, and it would check for which of those combinations work and produce a better performing model. If one particular one produces a better performing model, then that one is retained, and its results are compared against the next randomly selected combination, and it would go through that process iteratively until it reaches the specified number of combinations that you have asked that particular algorithm to stop at. So there's usually a stopping point where you specify that you'd want to stop iterating and checking. But again, at that particular point, you just get the best performing model. This model is not as exhaustive as the previous grid search technique. Grid search technique is a bit computationally, it's actually computationally expensive because you try out all the different combinations. But for random search, you just try out as many combinations as you have set to try out. So, and you will do that, and you will get to see how we can be able to do that with the scalar. And yeah, so you do that, and you also use cross-validation to just ensure you don't experience overfitting. And at the very end, you just select the best combination of hyperparameters with the best performance. This is usually a bit more efficient than grid search. And many people tend to use this because sometimes you could arrive randomly at a best set of hyperparameters, and you could end up just working with those hyperparameters. All right, lastly, Bayesian optimization. So this technique is somewhat different from these other two, but they have some slight similarity at the very beginning, where you would need to set the what is called the space, the search space where you would want to search your parameters. So you need to select the hyperparameters that you'd want to work with, and once you have been able to select that, you then so once you've selected, let's say you want to check for estimators between maybe 0 and 100 or 0 and 500 for different parameters that you want. What happens when you start using this Bayesian optimization algorithm? So what happens is that it selects a few random combinations from what you had defined from that search space, and then it builds another model, a model which is more like another computer that learns from now. So it learns from the results of these combinations that it has randomly selected. So first of all, you start with a few random combinations, you build that model. That model is called, you can call it a probabilistic model or surrogate model. And that model will now use the lessons or outcomes of the few random combinations that it got to now predict which other hyperparameter combinations would work best, and would lead to the best performing model. So it wouldn't now just select randomly the combinations to try out in the future. No, the surrogate model would look into its historical combinations, look at which combinations lead to better performing models, led to a better performing model, and then it would pick the ones that, based on its lessons or key learnings, are likely to lead to a better performance. So if a hyperparameter, a combination of hyperparameters based on the assessment of a surrogate model does not lead to a better performing model, it won't try out that particular set of combinations. It will try out those combinations that mathematically they look promising. So technically, when we are using Bayesian optimization, we are using what is called a surrogate model, and we would repeat that particular process of now of hyperparameter tuning using this surrogate model until we get to a criterion point or stopping criterion point, just like random search. That would be maybe the number of iterations that you have set or the time limit that you have set. So this is a whole lot more efficient. That random search just does it randomly. You can, in one instance you might get a better performing model, another one a poor and a better one. So that's generally it in terms of how these parameters work. And the next thing that hyperparameter tuning techniques work, the next thing that we're going to do is to go through now the practice work. In the video, you can check in the description link. There is a resources link there that will take you to a page that looks like what you're going to be seeing on your screen. You can download the sample practice resource and you can be able to now follow through. If you're an after-work member, want to commit more time to learning more about machine learning, we have all the resources that you need and recorded resources, and you could always consider just becoming an after-work member. So once you get to the sample practice resource, the first thing that you need to do is to go to File, then save a copy in Drive. Then you should be good to go. So I'll be using the practice notebook for this session. It has all the challenges, but for the sample doesn't have all the challenges. So once you have saved a copy, the next thing that we need to do, you could, because the beauty about using Colab, is that you have access to what are called GPUs or TPUs. And these are, you can think of them as just computers that are efficient. They help you to run most intensive code. Like what we're going to be doing, a whole lot of creation of just machine learning models using just hyperparameter tuning techniques. Then such comes into place. So what you can do once you get here, so let me first of all open my practice notebook in Playground. You don't have to do that. Once you have your copy of notebook, it's okay. So once you have gotten to have created your own copy of notebook, the next thing that you need to do, you can go to runtime, then change runtime type, and you can change it from CPU to TPU. TPU is just tensor processing unit. There are other GPUs that you can have access to, but you can, some of these things they're paid for, but by default you would be provided extra computational resources by Google if you use what we're using. So once you've done that, you can connect your notebook to Google servers as well as your TPU. Okay, if it tells us that we cannot, you current candidate, okay, we can just click on connect without if you get that option. But in some cases, you can be able to get TPU for free. It doesn't really cost much. But again, even the work that we're going to be doing isn't that as intensive as we would want. But yeah, so let's get started. Import pandas. All right. So once you've done that, let's now go to grid search, learn about grid search. We're going to load this data set. And our goal will be to use this data set to train a model so that it's able to predict an outcome based on the feature set that we have here. So we will perform some pre-processing. We won't need the patient ID column. We also won't need the blood pressure column as it is. We will need to convert it. So we will need to split it so that we have two new columns and drop the original one. So, and also convert the categorical variable columns into a numerical representation. We'll also drop this one. For now, we won't use it, medication dosage, but it's important. You can use it in healthcare. It's important to use it. Could be an important or determinant factor in our, especially when it comes to outcome. It's likely that medication would work, but for purposes of just learning how this particular technique research works, we're going to just drop it. So here we have systolic BP and diastolic BP, which are two new columns that we derived from blood pressure, and we split blood pressure to get those new columns as shown. So, and then we drop patient ID. We won't need that. Outcome, we will drop it for now so that we have our feature set. Our feature set does not have outcome. We also drop blood pressure. We also do the same thing for blood pressure. We drop it. Do you have, yes, this one, because we've already created two new columns out of it. And medication dosage, as mentioned, we're just going to drop it for now. But you need to convert these values to the respective values. Then we use an encoding technique called I'm forgetting the name of it. It's called one-hot encoding. So that's what we do here. By using get dummies. So one-hot encoding will help us to transform gender and cholesterol, and cholesterol into the equivalence. So let's do that. All right, so once we have done that, the next thing that we need to do is to split the data into training and test sets. Awesome. Then the next thing that we need to do is to define our model. By the way, some of these things are things that we've learned in the past, so you could always look at classification workshops, whether it's just classification analysis with healthcare or just classification analysis alone. You can check them out. All right, so here we instantiated the random forest classifier. Normally we would need to ensure that a decision tree based model such as this algorithm or such as this one, there's decision tree classifier that we can also use, etc. and others. So, but we will need to set this hyperparameter random snippet 42 so that we get reproducible results. Then we train our model using the training data set. And then here we just calculate its accuracy score. And here we have 0.46. Again, this is only for demonstration purposes. Our goal is to improve this. So to start off with grid search, we define our grid, which is just generally here, just the dictionary that has just several key values. The key values just represent the hyperparameter as well as the respective values, set of values that we want to try for that parameter. Then we define the model for grid search. So we will use this particular, just the same one, random forest classifier. And then here we import grid search CV from the sklearn library, and then we use it to be able to specify that we want to use this model to check for hyperparameters for its, which are these ones that we've specified, and want to use CVO. This just defines cross-fault 5, and then we now train our model using the data, testing out the different combinations, and the result will be that we will get the best parameters. Once it has finished training all the combinations, we'll get them here. This process I mentioned earlier can be computationally expensive. So you might end up waiting for a bit depending on how much time you have, or not even how much time, depending on the number of hyperparameter values that you've set in your grid. So if you've set maybe 10 values for maybe this particular case, you'll have to wait a bit longer because the number of combinations increases. The other way that could increase would be if you tried multiple more hyperparameters. So aside here we have 3, but if you tried more, you'd also get that you have a bit more. So you could pause the video and wait until it finishes, but I'll be talking through, just explaining what's happening. But ideally what we should get are the best parameters. So we should get, for n estimators, one particular value, for max depth another value, for mean sample split another value. That's what we should get over here. Then once we have finished that, we are going to now be able to use that model to then using those parameter values that we've got, the best ones, to predict. So to be able to reference the model, the best performing model, it would be grid search and best underestimator, and that will be our best model, and we can use it to predict now and calculate its accuracy score. And you can also use that for that case. So here you can see that the best parameters that we got were max depth none, then max sample split 15, so, and that's mean, then n estimators 200. So this combination worked best, and the outcome, we want to see whether it's going to improve from 0.467 that we have 0.533. So which, it's a better performing model. It has 53%. The previous one had 46.6. So yeah, so that's one technique, and you can try it out. So I have a challenge here. You can try it out. Do the same. Apply what you have learned, and then once you're done, we can continue. You can pause the video for that particular challenge. All right, moving on. random search. So we've gotten to learn how to work with grid search. We'll just reload the data set that we've been working with. So it's just the same data set. I won't go through the explanation again. I've already done that. So for the still, even for just being able to create our initial model, which is 0.466, now to be able to perform a random search, so we might decide to again, not even decide, we will set our hyperparameters, the ones that we want to check for. But here, instead of specifying that we want a grid search, in our previous example we had grid. So if I go up here, we had grid search, which is when we took our model that we set here. So here, what we're going to be doing, we're going to use random search, and we set the model that we want, and here we set the parameters that we want to check, and we set also our stopping point. Want to stop at this particular point, number 10. That's after 10 iterations. We set our cross-validation false, and also here we set just a random state. We do not necessarily have to, but we could always do that for reproducibility purposes. It's important. The previous case we did not, but yeah. So, and once we have done that, we are going to have the best parameters printed out. I've just run this because I understand it might take a bit, but it should be faster, because this just stops after 10 iterations. And yeah, so here we just predict the best model, and you can see best parameters found are these ones. These are another set of parameters than the ones that we used. And it seems as if the combination that we have here and also the combination that we got of parameters actually gave the same result, and a randomized search gave also 0.533, which is okay. Right, pause the video and then work on the challenge. And this challenge is only accessible to after-work members. So if you're not sure, if you want, again, you could always become an after-work member and get access to other resources. Bayesian optimization. So we mentioned that we use this type of model when we want to efficiently get the best parameters, and also this type of approach uses what is called a surrogate model, so, or a probabilistic model. So we will reload the data set that we had, but I don't think, okay, yeah, let's just reload them. And once we have reloaded them, we would actually create again our model that we had, 0.467, to use Bayesian optimization. The algorithm itself would need to install this package called scikit-optimize that contains the algorithm that we can be able to use. It will take just a few seconds, so we are going to do that. All right, it's done. Then we define the hyperparameter search space. So this is our search space. We want to define now where the Bayesian search algorithm will get its hyperparameter values to try out. And once we have defined the search space, we then again use our random forest classifier. It can be whatever classifier that you've identified to be the best performing out of the others. Then you use Bayesian search CV. You import the Bayesian optimization algorithm from SCOPT, or from the scikit optimize. In short, it's called SCOPT module. So we do that, and then we specify now the Bayesian the model that we want to use. That's a random forest search space, and we also define the stopping point. After how many iterations would we want to stop? Here we set our cross validation to just ensure that we don't have we don't experience overfitting. Then we set random state and we train our model, and then we print out the best parameters. Let me run this because it might take some time considering it's 50 iterations. We could have done maybe 20 for demonstration purposes, but yeah. So once we have gotten the best best parameters, which will print out, we then use that best estimator to predict and the X test, and use that for determining the accuracy score of our model. So this might take a bit of some time. You can just go take some coffee and come back. Should have explained it a bit earlier, but it's okay. I should have run this a bit earlier. But it's no worries. So let's wait. I can even just be talking about other things. But yeah, aside from this technique, this is the most, I think, advanced of the three. And you can also look at others. There are other techniques that you can explore, and also in addition to that, there are various packages that implement this type of this algorithm that we use. Let's say something like Bayesian optimization, even random search and grid search. There are other libraries that implement the same concept. It's just the same concept, just remains the same. The only thing is that people might write code or implement it differently, and provide that as a way of making your work easier. So you might find, maybe if you go through maybe online articles, you might read and get to see that there are implementations that look different from what you're seeing. Yeah, so don't worry about it. The process just remains the same. So let's wait for this as it continues, and yeah, let's give it maybe a few more seconds. All right. Yeah, it has finished, but now yours might have not. It depends again with even computational resources. Yeah, you can wait, you can pause the video because I'll continue after this. Just pause the video, go take some coffee, then come back. And even, by the way, this process can even take even 2 hours. So lucky that it has only taken this short, and that's because we just set the number of iterations to 50. Sometimes you might want to check out the possible combinations. Maybe you could end up with a combination that does work, that does lead to a better performing model. But you can see, even from what we have given it, is the search space, our accuracy, the best one we had is 0.533, and this set of combination, mark step 2, mean sample split 6, and an estimators 511 seemed to have been the best one so far, but it's still comparable to what we had for the previous options. So that's generally it. That's then you can just, by the way, copy these answers so that when, like, use these particular values. So when you are setting your model, so next time when you are using your random forest classifier, or you're instantiating it or creating an object, you could always set those values for the data set that you have, not for another data set. You have to use that data set, because even a change in a variable can mean that you have removed the best variable in a feature set that actually leads to the best performing model. So it has to be for the same one. So at this particular point, pause the video, work on the challenge. Once you're done, yeah, we can talk about the next steps. All right, so what's next? So what's next after this particular learning experience? You might ask. So as you can already see, these were learning outcomes, being able to define role and importance of hyperparameters in machine learning, implement different hyperparameter tuning techniques, as well as just evaluate impact of hyperparameter choices, etc. So once you've gone through this session, you could look into just applying just a few cases of we can look at maybe even just working on different problems and applying hyperparameter tuning techniques. You can also look into past workshops or past problems that you've worked on that involve creation of regression models or classification models, or even ensemble learning models, and tune those hyperparameters that you might find within those models and see how they would perform. Alternatively, you could look in, which is a good use case, you could looking into competitions. So looking to cargo competitions where you might be able to apply what you have learned. The goal of those competitions, those machine learning competitions, such as cargo, or even another one called Zindi, is to create a machine learning model that performs best or better than anyone else. And in that process, you will end up performing these hyperparameter tuning techniques. You will exhaustively perform those hyperparameter techniques because your mind will be just, I need to get the best hyperparameter techniques given the following constraints. And you might even realize that you would end up even not only just building models, you might end up building basic ones, but even doing research, or maybe you could get other advanced models such as ones that entail ensemble learning, and those ones would help you just build your knowledge in machine learning a lot. So looking into competitions, read about how other people have been able to go about improving model performance. And if maybe you haven't even done feature engineering, that's also some other area of growth that you could look into, and ensure that you work on projects. Projects will help you to be able to do much, especially when you create even a project or decide to work on an open source project that helps people real life, that solves for real life problems. So we could look also into real life use cases around within your community, around maybe with regards to problems that are there, and once you've determined that a machine learning model is the best solution for that, then you can build that machine learning model and end up creating a solution that you could open source and post it on GitHub, on your GitHub account, provide a good documentation, spread the word to people, look for people who might be interested in your solution, and keep on developing after maybe a few weeks or weeks, keep on improving your solution. Over time, you will actually have gotten to have practiced enough this concept, the concepts that we've learned so far. So that's it with regards to this workshop. I hope you are able to have achieved these learning outcomes, and we've set you up for success in your projects. And we hope that we'll get to see you again. If just an ask, if you loved the learning experience, if you thought it was quite informative and invaluable, and other people might benefit from this particular learning experience, you can give this video a thumbs up. It also tells us that we're doing something that we need to keep on doing. So give this video a thumbs up. Just takes just a click. And also, if you'd want to be informed when we post such future videos or even on emerging technologies, you can always subscribe, and see you the next time that we see each other. All the best in your learning journey. Bye-bye.